welcome from my side. It's a great opportunity for me to talk here about how to measure energy efficiency in the building part. Also because the core of the results of this presentation is more thought-provoking, explorative style, and some of the results are actually from the master thesis from Sarah, which just introduced me, so it's a very nice coincidence. So first, about our company, Geoimpact, we are a Swiss-based company, we work in Switzerland, and we collect a lot of data in the energy and building area. It's open government data, we parse data sources, we have data from our customers, and from data partners we bring it all together, and then we do data analysis, process them, make them available over APIs to the customers, we do event notifications, integrate it to the websites of the customers, into their workflows, and two applications were already mentioned. The main app is called Swiss Energy Planning, so if you are more interested in this, I encourage you to go and check this out. And then we provide it to the use cases, and the use cases are quite diverse everywhere where this ever-growing data can be used. It's in finding potentials, in planning, using data in consultation of customers or also citizens, if the customers are or municipalities, and so on. And also there's like a small feedback path when the municipalities are actually maintaining their government data, we also assist them in doing that. So, as a jump into the topic, energy efficiency in Switzerland, a recent event is the Federal Act on Secure Electricity Supply with Renewable Energies, which is now term Mantelerlass. It was just passed in last September, and it's still due to be accepted by the popular in referendum, so it's not even sure if it will be applied, but hopefully it will. And there is, among many topics, there's also one topic about energy efficiency. So it says that electricity suppliers must realize electricity savings through energy efficiency improvements amounting to 2% per year. So this is a concrete topic which will probably soon be of interest to the utilities. And it also says something about the measures. So the measures are only permitted if these savings can actually be measured or calculated. So for me, the question pop up first: how large is the savings potential in Switzerland? I'm also interested here more in the building part, but overall energy savings potential, not only electricity. Then which of these potentials can actually be measured, and how large is the overlap? Because although the English language suggests that measures are measurable, it may be a surprise that today maybe not all measures are actually measurable, and this act, of course, only acts on the measures that are actually measurable. So first, a short overview over the potentials. So this is just for buildings. A big part is heating and hot water. So we have thermal sources, which is non-electric, and electric sources. And yeah, there we have a big potential of up to 64% through building envelope measures. And another even similar high potential by switching from current heating systems, oil or electric radiators, to heat pumps, for example. And then in the lighting, we also have a very big potential, also big potentials in appliances and households and system processing companies. So I stretched these numbers together to show you that the potential is really impressive, but also some caution is to be applied, because in reality you probably will observe lower effects actually due to different effects which are known under names like energy performance gap, rebound effect, comfort factor, and so on. now a short philosophical excursus about measuring efficiency. So measuring you always do by comparing different things. And for efficiency, it's not so clear to what you should compare. And you have two ways to compare. So one is comparing over time, one object. You look at different time steps. Then you maybe measure the consumption reduction in percentage. These are the numbers that we have seen. We have always, so far we have only seen percent. The problem here, when your object is a region that you want to track, there will be many structural changes which don't have a real connection to efficiency, but still affect the consumption. So it's hard to entangle the efficiency from the structural changes, like new companies, new buildings, and so on. So there's another way you can compare different buildings with each other. And here, the way is to define some performance indicator. For heat demand, it's called specific heat demand. It's a common indicator where you divide the heat consumption by the energy reference area. But you could also normalize by inhabitant for electricity or by employee for consumption. So there are different possibilities. And here the difficulties are that also buildings are always structurally different, so they are never really comparable only to efficiency. And also the indicators, some buildings might be more efficient when you divide by the area, others by inhabitants, so these indicators introduce some kind of bias into the efficiency notion. So now we want to propose a framework to kind of entangle these numbers into the different effects of measures. So this is like the framework looks like. So we have here the structural data. So this is the data that we ideally would have or almost have already today, I would say. So there's structural data about the building. Then there are different operational measures that you apply on this building. So either you calibrate the heating system, you replace the window, you insulate the facade, or you replace heating systems like technological measures. And then on the consumption side, we have yearly heat consumption measurements. And yeah, I would say it's almost impossible to measure all these measures separately with different meters actually. So the idea here is to connect it with a machine learning model, a heat demand model. So for this structural data we have, and later we will see how we try to extract the measures, envelope measures from building application data. And then for one more statistical tool for this separation to check the effects is called partial dependency plots. Just a short note on that. So you have usually one or two features, XS, that you are interested about, and you have a function F. This could be the trained heat demand model we just said before, or you could use any function of the input features, and then you do an expectation over all features except XS. So now I'm going to show you how it looks like. So here two examples for two attributes, construction year and heating degree days. So in orange you see the partial dependence of these attributes on the specific heat demand. So we divided the heat consumption model by the energy reference area, then you see the dependency on these different attributes. So for construction year, you see that newer buildings around year 2020 are much more efficient compared to older buildings. And in dotted lines, you also see other values from literature. There is some correspondence, but also some deviations. So for now, I just leave you with that the deviations can be attributed to the different data sets and also to the different methodologies. But just to get an idea how this dependency looks like for such attributes. And now, the interesting part I already mentioned is the results from the master's thesis So where we applied the same framework to measures extracted from building application data. So in the column here, you see the left column, you see the results from the thesis, for example, for window replacement. Buildings that had the attribute window replacement extracted from the building applications have between 3.4 and 5.1 kilowatt hours per square meter per year lower specific heat demand compared to buildings without this attribute. And yeah, the two numbers come from two different machine learning models that we used in the framework. And on the right-hand side, you see numbers extracted from literature. They also went some way, but they come from the CECB, which are these building certificates. From there, they extracted how much these measures take, and then they extrapolated it for whole Switzerland. And yeah, we see quite some deviations again, and here the deviations can be attributed to two effects. So first is data quality. So in the master thesis, we were actually interested in to check if the building application data can be used for this purpose. And probably the big difference says that it's probably not has not the required depth and coverage, because this data is not collected for this actual purpose, but for another purpose. So we tried to apply it to this new use case, which, yeah, so it's a test. But then the other attributes, if the data could be trusted, then would be that is now what we have seen, observed. So our columns are observed data versus the literature values, which are based on future estimates. And so then, ideally, the deviation would be only due to performance gap, rebound effect, comfort factor, and so on, what we would actually be interested in. So what I want to emphasize is that our values here could already today be actually continuously monitored for all the buildings where you have the consumption and these attributes. So, and you could also apply it for your efficiency monitoring if it will come. Yeah, but at least it would be possible. So the conclusions, we have seen that building efficiency measures occur in many different events, and the effects of them are hard to track separately. And we proposed a framework to separate these effects on the consumption and specific heat demand based on the machine learning framework. And yeah, this framework could also be extended to electricity consumption. There it's even a little bit more difficult because there are even more influential factors for electricity demand, but basically possible. And we have seen that model selection is important. So there is the machine learning model. We have seen the two different values. So we should also take attention on the models, maybe try different models. And data quality is of course important. Yeah, for consistent tracking of these effects, we need building structure data and the applied measures and the yearly heat consumption, which, yeah, I would argue is a minimal set required if you want to actually measure efficiency in many building like heat consumption and electricity consumption. It's just my view. You are allowed to challenge that. And so, ready for Easter, I want to finish with the chicken and egg problem of data quality. So, here data quality is the egg and the chicken is the use cases. So, in order to build good use cases, you need good data. And on the other hand, in order to take the cost and effort to produce and maintain quality data, you need use cases to be motivated, right? You don't just start with data. So At Q-Impact, we are especially working on the upper arrow with the current data. There is already a lot of data available. So we show use cases and hope to inspire and also give a vision to the people who are, have more leverage on the data quality. And we hope that it's going to be an upward spiral.